Okay, so basically root locus is a concept which is derived from our previous concept. Let us consider that there is a feedback system. Say input is denoted by R of s, G of s is the open loop transfer function. You have C of s as the output. Let's say there is a feedback with gain h of s, and let's assume that this is a say negative feedback. Okay, now in such case the characteristic equation is given by what is the characteristic equation? It is 1 plus g of s into h of s equals to 0. Now we know that the open loop g into h includes a particular value called gain, right? That is denoted by k. Already we have seen in the previous case that in say uh, in pole zero format, what is the standard g into h looks like? G of s into h of s. This looks like a value k into the zeros will come into picture, zeros of the equation, correct? So this is s plus z1, s plus z2, and so on, many more. That's the numerator part, and in the denominator we can have s plus p1, s plus p2, and so on. Okay, let me write the one of the last term. There can be, let's assume that we have m number of zeros. So this is zm, and let's say there are n number of poles, so this is s plus pn, right? So this is the pole zero format of the equation, right? So now uh, we saw that in one type of problems we understood that as the k varies here, right? We knew that, okay, I'll go back to the question. So we solved some problems that find the range of k for which the system is stable, correct? If you recall. So that means as the value of k changes, right, stability changes. This is first point, right? So now I'll write one point here. So as k varies, this implies stability of the system changes. This is one point which already we know. Okay, the second point which I want to take from the previous discussion is that we know that on the S plane, right, if the roots, in the sense if the roots of the characteristic equation, that is if you have poles present on the right hand side, then also stability will change, right? So let's try to relate both of them now. So the second point is if poles on RHS of the S plane, this is also going to, right, change the stability, right? So this I'll directly write unstable. All right. So now let's try to relate these two to bring in the concept of root locus now. So this means the 2 points which we have mentioned just now, it actually indicates that when k varies for some ranges of some values of k, maybe 0 to 10, let's say, system is stable means all the poles are present on the left hand side. Okay, but for some other range, maybe k greater than 10, we understand that system becomes unstable means the poles are going to move to the right hand side, right? So that's the only indication which when we club the two concepts here, because as of now we studied simply, okay, k is something and the poles are something different, right? So far we consider that, okay, both are different concepts, but stability is the same, right? We are talking about the stability of the same system, which indicates that, okay, these two different aspects are ultimately going to be combined together to get a single concept of stability. So when k, we say that, okay, k for this range of k system is stable means all the poles are present on the left hand side, right? For some other range, when we say for this range of k system is unstable means, right, poles have to move to the right hand side, then only system becomes unstable, right? So this indicates that. So let's write a point now. So as the k varies, this implies, right, the, I'll simply write the roots, okay, roots of the characteristic equation, right, they move on S plane. Right. For some range of k, stable, some range of k, is unstable. Now, the plot, right? Now, the plot that we can try to plot by varying the k from 0 to infinity. Because for some system is stable, for some other value, system is not stable, right? If we try to, we have a equation now. Let's assume that we consider a system and we have a equation of representing the system. Now in that equation you will be given a k itself. There is no value specified because our intention is to visualize what happens to the system's roots, right? When I vary k from 0 to infinity, k equal to 0, the roots are here, k equal to some other value, root reaches some other point. When k is equal to say infinity, root reaches some other point on the S plane. If you try to plot such a graph by varying k from 0 to infinity for any given equation, right, for any given g into h, whatever graph you get, that graph is called as the root locus. Now it makes sense, right? Root is the root of that equation. Locus is all the set of points it's going to cover on a given particular plane. Okay, so that's the definition of what is called as a root locus, right? So the of plot of the locus, or I can write in plural, okay, locus of roots of a given g of s into h of s by varying k in the sense the k will be present in any given equation. Okay, so there will be a k always when the question is to plot a root locus. Okay, so by varying a k from 0 to infinity, this is called as the root locus for that given system. Okay, now again I can give another explanation why you get multiple points here, and something like, okay, maybe the root locus might look like this, possible. Okay, now you see that I have many points. I am saying that when maybe when k equal to 0, this is a root. When k equal to infinity, these are the 2 points, right? So I connect in the middle, k equal to 1.5, k equal to 2, 2.5, 3 point, like that I connect. Why do you get so many points, right, for this, right? Yeah, when you vary k, right, why do you get many points is my question. Okay, so there is an answer for this, right? There is a different way of answer. Now anyway, I know that one simple explanation we already have covered that. Okay, there is another way to express the same thing in a mathematical format, maybe. Okay, your college, or if you refer any of the textbooks, you might see this answer. Okay, both are valid. It is because let's start with the characteristic equation. This is uh, another explanation for what we already have discussed. So the characteristic equation is 1 plus g of s into h of s, right, equal to 0. Now you see that this indicates that what is g into h? G of s into h of s can be written as -1, but -1 can actually be written as in a complex number format. This is -1 plus j0, right? So this j0 is actually, if you try to represent in polar format, right, this is actually one angle 180, correct? But this is actually also equal to one angle. I can try to write it in a different format. This is sum 2q plus 1, any odd number, into 180, correct? Any odd multiples of 180 will definitely come to the same point, correct? So you see that for several values of q, I keep repeating the same thing, right? I keep getting the same thing. This 1 plus gh equal to 0, this characteristic equation gets solved for multiple values of q, right? There are different values of q, right, for which this equation is getting satisfied, right? Which means there are multiple values of s, right, satisfying the condition. Multiple values of s means what? It's a point on the s plane, right? Correct. So that's why you have multiple points that come up. When you add all of them together satisfying this condition, you get the root locus. All right. Okay, so this implies, I'll just write quickly. So multiple points on s plane, right, satisfy, right, the condition, that is g into h. In short, I write, if you take a magnitude equal to 1 and the angle is definitely, right, 2q plus 1 into any odd multiple of 180, this condition gets satisfied by multiple points. When you connect all the points together, you get a root locus. Okay, so connecting all such points means that itself is the locus, or the locus of roots of the equation. Okay, hope this is clear, right? So this is the simple introduction we need before we go into the concepts, right? Okay, now when any equation is given, right? Say some g of s into h of s is given for us. Normally the question will be like that: plot the root locus of so and so system given by a equation. Now, what we need to do? Let's directly go to that. Okay, so I'll directly write the steps we need to follow to plot the root locus. Right. So whenever the equation is given, right, we have to identify, right? Anyway, when an equation is given, we can definitely find out the number of poles in the equation and number of zeros in the equation. All right, so we always find, the first step is to find the number of poles and number of zeros in the equation. Okay, all right, so this is, say, okay, I'll write a number so that we can identify the steps by number. Okay, step number 1 is from the given g into h equation, right, find the poles. First we find the poles, and also we find the zeros. Okay, and let's say that there are number of poles. Okay, I'll write find the poles and zeros. So let's denote, let say P is the number of poles, Z is the number of zeros of that given equation. Okay, then what we can find out from these numbers P and Z, anyway P will have several values. Okay, like if you have two poles at 2 and -2, there will be P1 P2, and the value of capital P is equal to 2 because there are two poles, and poles are located at different locations. You can give any other notation for that, P1 equal to something, P2 equal to something, and so on. Similarly, Z holds the number of zeros of the equation, and Z1 Z2 Z3 will hold the values of those poles. Okay, now in the step 1 we always identify how many branches are there. Okay, so then branches of the root locus, how many branches you can have, right, is equal to, this is equal to the maximum number out of these two, max of P and Z, whichever is highest, so many branches will be there. Okay, this is the first thing. No, it's just G into H, because see, this equation is what we are considering, this one, this format. Okay, now fine. So in the next step, let's okay, I find out how many branches I have. Okay, the total number of branches I got now, and out of these branches, right, let's say this is 2 and this is 3. In that case, the total number of branch become equal to 3. Correct? Now, out of these, out of so many branches, some branches will go to infinity. Okay, in the sense, let me give a quick example. Let's uh, say there is one pole and one zero. Let's assume that I have say 3 poles and one zero. Let's say in such case. Okay, uh, what happens here is, let's assume like this. So 3 poles I marked, one zero I marked. Now the root locus will be, actually when we solve you will understand, right? You get something like this. So this goes to infinity, this also goes to infinity. So you see that two branches will go to infinity in this case, and one branch is not going to infinity. It's a finite, right? So you see that how many branch in this case, two branches are going to infinity, right? And since can you tell me the number of poles here? Poles equal to 3, right? So you see P equal to 3. What's the number of 0? 0 is equal to 1, right? Now it's very clear that how many branches you have, it is maximum, that is 3. So 1, 2 and 3. Okay, and the number of branches going to infinity is the magnitude of the difference. Correct? So difference is 3 minus 1. Okay, 3 minus 1, so I have 2 branches. So then this is just an example, we'll solve a problem just to make it clear. Okay, so then branches going to infinity, towards infinity, okay, is equal to, I simply, it can be P minus Z or Z minus P. I'll simply take a magnitude. Okay, P minus Z, magnitude of poles minus number of poles minus number of zeros. Okay, so in the first step, I come to know about the plot that we are going to write, right? We keep getting details, more and more details as we go to different steps. In the step number 1, only I have an equation with me. My intention is to plot a graph. I keep extracting the details, right? Initially, I get these two details. How many branches I have, and out of those many branches, how many will go to infinity? I'll come to know. But I cannot plot. What I can plot is, I can simply plot the poles and zeros presented, present on the S plane. I can simply plot them. I cannot plot anything else, right? As of now, in the step number 1. Okay, so we mark poles and zeros on the graph. So this is what is included in the step number 1. So plot, or I can say simply we'll mark. Okay, so this is mark poles and zeros on the graph. This is the step number 1. So we get some details and we do something. Okay, right. In the step number 2, this is step number 2. All right. All the branches, whichever, how many branches we know now, each and every branch will start from a pole and goes towards a zero. Okay, so a branch, it's always starts at a pole, okay, and goes to or goes towards a zero. Fine. In the sense, anyway, this is again an example. I have a pole here and I have a zero here. Let's say, okay, pole at -1, zero at -2 for some equation, g into h. Now, definitely, I will mark a root locus here, right? Why this point is given? Because if at all you mark something, you have to give an arrow mark from where to where. So it is always starting at a pole and going towards a zero. That's why just to put an arrow mark on the root locus, because root locus, we know that locus means it's a collection of point as k varies from 0 to infinity. So it starts at a pole, goes to the 0. Okay, now we have, right, let's go to the previous case. Right, let's go to the previous example. You see that there are two branches going to infinity. Now can you tell me why those two branches are marked as going to infinity? Definitely I'll mark something like this. Okay, it starts from a pole, two poles which are marked here, and the root locus is already marked. I actually add up an arrow like this, indicating that the zeros are assumed to be present at infinity. That's why they go to infinity. Okay, so when you don't, I don't see any, see in this particular case I see only one pole, but I have two more, sorry, 1 0, my mistake, there is only 1 0, right, and I am expecting two more zeros because there are two more poles, right? So when you have two more poles and there is and we don't find any, what you call, any zeros to compensate those two poles, we assume that okay, those two the required two zeros are at infinity, and that's why whichever branch starts from such pole will go to infinity. Okay, so that's the reason why we are actually plotting like this. Okay, right, now let's proceed further. So where were we? Okay, this is the first one. Now I add up the other point which we just mentioned, right? If you don't find a finite zero, okay, branch will go to infinity. Starts at a pole and goes towards a zero. So we have two subpoints here, and again they are optional. We see the problem. If it is applicable, we'll apply, otherwise we leave. Okay, so in case of no finite zeros, like the previous case, right, so there was only one finite zero and other two zeros were not existing, we assume that branch will go to infinity because zeros are present at infinity. Okay, in case no finite zeros, then branches go to infinity, right? So how many branches will go to infinity? Anyway, we already have calculated in the step number 1, right? There is a opposite case, like if at all you don't have finite poles, right? What should happen? What do you expect? Let's say in this point I mentioned that in case of no finite zeros, so and so thing will happen. Okay, now I change the point. In case of no finite poles, but I have to have so many number of branches for sure. You cannot skip that point, right? In the sense, I already made a point, something like this. Let's assume, right? Let us assume that we have the reverse case. I have a zero here, I have a pole here, and I have two zeros over here. Okay, right? So my rule says that okay, there will be a pole to. Yes, yes, yes. That's all. That's all. Right. So now you see, you assume the poles to be present at infinity, and the arrow marks will be towards the zeros. That's all. All right. So that's the next point we have to add here. So in case of no finite poles, then branches come from infinity to those zeros. Okay, fine. Now we have another point to come up. So in this point, we get few more details about the graph. Okay, so now so far we know that, okay, so how many branches, how many will go to infinity, what should be the arrow mark, right? What should be the direction? But again, I cannot, if I see a diagram, like if I see the poles and zeros located like this, I cannot plot this directly, right? Why only this way? Because infinity can even come from this side, right? Right, even maybe multiple, you have infinite answers possible, right? But how do you bring, how do you eliminate all the other possibilities and come to a single graph? That's what we need to investigate further. Okay, so now we have another point coming up, that is next 2 points will make a few more things very clear. Okay, the one thing is that this okay, I'll write it as a point number 3. Okay, this is how we write. I'll add a small point to the previous one. It goes to infinity or comes to infinity. There is another term to be added. Okay, I just missed that. I'll add up here. So goes to infinity. This is mathematical word. Asymptotically. What do you mean by that? Have you heard this before? Asymptotes. Yeah. Can you define what an asymptote? Okay, yeah, very close, very close. I'll come to that. Okay, so I'll add the word here as well. So in case of no finite poles, then also branches will come from infinity to zeros, again asymptotic. Okay, right. Now this is one idea, that you cannot have multiple asymptotes. Okay, asymptotes are very finite and they are very rare, right? If you find an asymptote, now along the asymptote, whichever curve you draw, right, that will be a single curve, right? So that actually eliminates all the multiple answers which you write like this, right? Because I have only one asymptote, possibly this one. So if this is an asymptote, only this is the possible answer. I don't have any other this thing, correct? Because asymptotes have some characteristics like, okay, before writing the point, I'll make that clear. So if at all I draw an asymptote, let me draw a graph. Okay, let's see. Let me say there is a curve like this, and the asymptote, which if you draw, say, okay, I'll change the color, maybe. Okay, I say this is, maybe this is an asymptote. Let me assume. Okay, let me say this is the asymptote. Okay, so it means this, anyway, this goes to infinity. This curve is also going to infinity. They are going to meet at infinity. Nowhere, nowhere before infinity they can meet, right? Which means it's a unique line. This straight line is very unique for a given curve, right? They are never going to cross each other. Like this crossing and meeting at a point will never happen until and unless we reach infinity. That such a line, such a straight line is called as asymptote of a given curve, right? That's why this concept is important now. So I have to now the point is I have to find out an asymptote for the required set of poles and zeros, and I have to draw the curve. So since this curve is very unique, the all the multiple, what you call, multiple solutions get eliminated. Oh, for a given asymptote, you have only one curve satisfying the conditions of asymptote. That's why you have only one. Now, if I have two branches going to infinity, it indicates that you need to find two asymptotes, right? That's why first step itself, I find out number of branches going to infinity. Okay, so when you have that number with you, you know now that, okay, I need to find, okay, there are three branches going to infinity, then I need three asymptotes to be found. Okay, we draw the asymptotes on the graphs, and along the asymptotes we draw the curves satisfying the conditions. Okay, so that's one. Okay, so this point is clear now. So let's go further. Now, before we draw anything on the graph, right? Our first drawing of the root locus will start on the real axis. Okay, if you have a curve like this, on this real axis, do I have to plot root locus or not? This is what I need to decide. Okay, but before drawing that, I need to remember one more thing, right? This is what I'm going to write as point number 3, I guess. Okay, so let me just say, yeah, this is point number 3. The root locus is always symmetric about real axis. It's because the if I have g into h is equal to -1, that condition will be satisfied by, if s is complex, then you always get complex conjugate roots, right? Complex conjugate means one point above x-axis, one point below the x-axis. So you see that whenever you get two roots, right, they are always complex conjugates. So distance of complex conjugate roots are equal with respect to x-axis. From x-axis, the distance remains same. Correct? That's why it is symmetric, right? I might have infinite points satisfying the conditions, right? So all those points will be equally distanced between equally distanced from x-axis. That's why it is symmetric about real axis or the x-axis. This is the point I need to remember. Now you see, now it makes sense why I try to draw something like this. So it actually, you see, it started from here, it's going here. I also start from here and it goes here. So it's these points are complex conjugates. You can see, correct? Okay, right. Let's go ahead. The always I just have to remember. So the point number 3, it's just for before we plot something, we just have to satisfy this condition. That's all. Okay, right. So point number 4. Now we actually start plotting the graph. The graph lies on the real axis, right? For certain conditions. Okay, the root locus lies on the real axis if the total number of poles and zeros to the right side is odd number. Okay, so I'll make this clear now. So I just have to check that whether the root locus lies on the x-axis or not. It lies if the total number of poles and zeros, it's actually, this is applicable for a given point, it's not for the whole x-axis. I'll make the point clear. Okay, so let me draw something. So let's say that I'll draw two different examples. All right, so it could be something like maybe I'll draw the poles and zeros here. So poles, zero, maybe a pole, and another pole, maybe another zero, something like this. That's it. Okay, so now I'll see. So so this whole line is my real axis, but the whole x-axis will never contain the root locus. Okay, now the part by part I need to investigate. So I'll start from this side maybe. Okay, I want to decide that in along this line, do I have to draw the curve, do I have to draw the root locus or not? So what I should do for this complete given region, right, look at how many number of poles or zeros are on the right hand side of this given part of the x-axis. Do you have? You don't have, right? So total number of poles and zeros to the right side of that portion of the x-axis, right? Do you have any poles or zeros on this side? No. So which means this part of the x-axis is not going to have any I'm not going to plot, right? Root locus will not lie over here. Okay, I move further. So what I do, I consider this portion now. In this portion, take any point and look at the number of poles, sum of the number of zero. There is one pole but no zero, so it's an odd number, correct? So whenever you say this is an odd number, which means yes, here you have the root locus, and it makes sense. Always starts from a pole, goes to a zero, right? Now I come to this portion. What's the sum? Sum is a even number, so I don't have a graph, right? In this region, I don't have a graph. Okay, I come to this now, right? This you have. Okay, so yes, my condition always is true. So it's a pole to pole. I have a different point to answer this particular part, but yes, there is pole, sorry, there is root locus. All right, so as per the rule here also, it actually starts, there is a branch starting here, there is a branch starting here, but something else will happen in the middle. We'll see that later, because for two poles I am expecting two zeros. Do you have two zeros? No, correct? I don't have two zeros, so we expect the pole to be present at infinity. Actually there is the two lines will go like this, right? This is called as a breakaway, break in, etc., right? We'll come to that later. Okay, but as per the rules which we studied so far, yes, there will be a branch, right? Actually there are two branches, because two poles means two branches will start from two poles, right? Since there is no finite zero satisfying the condition here, so there will be branching and they will go to infinity as per the rule, according to by using what is called as asymptote. We have to find two asymptotes here. Okay, but that's not our point as of now. So anyway, in this region there will be root locus, correct? Next, come to this region. It is even number, so there is no root locus, correct? But for the last one, do you have root locus here? No, you count 1, 2, 3, 4, 5. Odd number, right? Everything to the right. Everything to the right of that, right side of that region. Whichever region you are considering, you should count the total. That's why this point is important. Total number of poles and zeros. It's not or, okay? And zero. So it's a sum to the right side of that region, whichever region you are considering. All right, so definitely it has to come. Now you see that again the point which we made earlier is clear. There is no finite pole, so we are assuming a pole at infinity. At infinity you assume that there is a x, so from there that branch originated and it is coming to the 0. All right, okay, so that's this point. Root locus lies on real axis under some condition. Okay, now okay, so this is point number 4. Let's move on to point number 5. Now we know that if at all you have uh, you require asymptotes because you have many branches going to infinity. So number of branches going to infinity is already decided, and I know now how many asymptotes I am supposed to find out. Right, so in order to find out that, right, I need what is called as a centroid, right, because all the asymptotes will come and meet at the same point. That is called as a it's called as a centroid, right? So to find that we use an equation now to find the centroid. So this point, but this particular point, I think this is point number 5, I guess. Okay, the point number 5 comes into picture only if your problem shows that I need so many number of asymptotes. Only if you need asymptote, you calculate this. Otherwise, your problem becomes simple. You don't have to find it. Okay, so all the steps are actually it's not fixed for every problem. Okay, it changes from problem to problem. When we solve, it becomes more clear. Okay, so this is point number 5. To find the centroid, what's the meaning of centroid? So where all asymptotes of the root locus meet, they come and meet at the same point, because this is very helpful. I need to find this because from which point they start. If I need 2 points in order to draw a straight line. I need 2 points. One of the point will be this one. Okay, so how to find the second point we'll see later. All right, so this is the equation. Okay, so that is uh, sigma. This is denoted by sigma. Sigma is equal to the sum of, I have to find the first I'll write the poles. Okay, sum of, I'll write finite poles of the given equation. If at all you expect a pole at infinity, we don't write that because this whole equation becomes infinite in that case. Okay, so that's why it's a sum of finite poles minus sum of finite zeros whole divided by, this is the number of poles minus number of zeros. So for example, if you have the poles P1 at 2 and P2 at say 3, okay, and let's say zeros, Z1 at -1 and Z2 at some other value, say -5, and say Z3 is equal to some other one. Okay, maybe 4. Now what you do, this finite poles, sum of finite poles is 2 plus 3. Okay, sum of finite zero is -1 plus -5 plus 4. Okay, that number will, the sum will come over there, but this is simply the numbers. Number of poles is 2, number of 0 is equal to 3. So 2 minus 3 is -1 in the denominator. Okay, so we just have to substitute in this manner to calculate what is called as the centroid. It's always, it's going to be a real value. You can see that, right? We don't get a imaginary or complex number. So this point will be on the x-axis. So since it is real, it's only on the x-axis. Okay, so now let us assume that I got a point, right? So I have maybe something like this. I got a centroid. Let's say this point, say centroid came to be -1.5. So I mark the centroid. Now let us assume that I need 3 different 3 or 4, let me assume, let me assume 4 branches. I am expecting 4 branches, in the sense, because 4 branches can be anything like this, right? This is 1 2 3 4, fine. Or you have other options also, because you have infinite solutions. I can draw 4 lines going to infinity from this point, because I'm expecting 4 branches going to infinity. But that those 4 lines can be drawn in any fashion, right? So now we are actually looking for specific answers, right? How do you find out? For that I need second point. If I have a point here, then I can connect like this. This is line number 1, asymptote number 1, going to infinity. Okay, if I have another specific one here, then I can connect. Now you see, you have a specific answer, right? I cannot write any possible solution out of infinite solutions. I cannot write it, right? So for that reason, now we go to the next step, right? That is finding out the second point. Either you need a second point or you need an angle. So draw a line making 60-degree means it is fixed. You see, this is fixed. I cannot draw a different line making 60-degree, right? So maybe the second one could be draw at 120-degree with respect to x-axis. That is only one straight line. There is, I cannot write multiple straight lines making 60-degree, sorry, 120-degree with x-axis. Not possible, right? So because of that reason, now instead of finding the second point, we find out the angle. Okay, this is called as angle of asymptote. So this is denoted by phi a, asymptote. Sigma is actually, normally textbooks will call sigma a, because it's the centroid corresponding to the asymptotes. All right. So normally phi a will be present in the, they are going to use it as a phi a in textbooks. So I'll write that. So, and it's the same point, angles of asymptotes, denoted by phi a. We can calculate the phi a. It's 2q plus 1 into 180 degrees whole divided by p minus z. So p and z still same, the same. Okay. So the q value will be 0, 1, 2, dot dot dot. So how many values you put, that depends upon how many number of branches you look for. If you are expecting 3 branches, put only first 3 values, 0, 1 and 2. Okay, you are expecting, normally say, it's in the same order. First one will be corresponding to 0, second one will be corresponding to whatever answer you get for 1, and so on. Okay, first asymptote makes, you get an angle corresponding to 0, second asymptote corresponding to 1, whatever value you get here. Is it okay? Yes. Fine. So using this you get, so if I'm expecting 3 branches, 3 asymptotes will be obtained from here, 3 angles. First point is already known. You find 4 different angles, you get 4 different asymptotes. That's all. Okay, so when we have, now we actually have more details about the graph that we are supposed to draw, right? Because let's go for a simple example, like this. So let's assume that I have, okay, let me draw something like 1, 2, let's say simple case. All right. And in this case, I know that there will be root locus here, because it satisfies one of the condition. The next one is like this. So this one is anyway already going to infinity. Okay, but still it needs an asymptote now, because whenever you don't have a, what you call, finite zero compensating a finite pole, it means there is a asymptote required. Okay, now let us assume that I use these values, the position like -1, -2, and say this is -5. Use these values, number of poles, number of zeros are number of poles equal to 3, number of 0 is equal to 0, and I apply the equation, and let's say assume that I find a sigma value somewhere here. Okay, so this is the sigma. So you solve, and the angles come as a 60. One will be 60, one will be 180, and one will be like this. Okay, you get three this things. Okay, so corresponding to, because you expect three different asymptotes, right? So asymptotes will be like this. Okay, this is what you get when you solve, right? Okay, now I know something. Now you see how you decide the shape, because from the -1 and -2, there are two branches originating from -1 and -2, correct? Now what happens, both of them, there are two branches. This results in what is called as a breakaway point. Okay, that's my next point, but anyway, I just have to tell you how do you decide the shape now. So anyway, I know that one branch is going to infinity, one more branch is also going to infinity. I already know that whatever I draw here, I should be copying the same thing below because it is symmetric. That's my first point that I'm going to use. I also use a second point, that the asymptotes are already drawn here. Means whatever branch you draw here, right, it cannot cross here. Correct? That's what is asymptote, right? It cannot cross that. So I already know that it cannot cross. So now you see it has to be drawn like this only. I don't have any other option. When you draw one of the branch like that, the other branch also has to be drawn in this way. Correct? Isn't it? So that's how you decide the shapes. Anyway, we have more points to support this, that they are coming up. You can actually find out the intersection, right? Indicating that, okay, the branch which started from here, where do they cross the y-axis? It has to be purely imaginary because it's intersection with y-axis, which is imaginary line. Once you get a plus j3, you will definitely get another route as minus j3. We'll justify this. Okay, also you have another point that is coming up now, which tells you that where is this breakaway happening, because it has to be between -1 and -2 only, right? You will draw an equation from the given g into h, and you solve some condition, you put some condition to that equation, and solve that equation to get several sets of points, right? When you solve a specific equation, you may get the roots as -1.5, -0.7, and say -2.5, right? So it says that the condition is met by this, but you will select only this because I am expecting the breakaway happening between -1 and -2. So other points you neglect. Okay, so the condition will come up, will be coming up in the maybe point number 7 or 6, I guess. Okay, right? So anyway, we covered only half of the required points. Now there are actually 8 to 9 points to be discussed, right? Then we can go to the problems.